Welcome back to another session. Today we want to look at motion. And another word that we can look at when we talk about motion is what we call kinematics, and that is pretty much the study of motion, so to speak. So in our Unit 1 syllabus, we are going to study motion. We're going to look at terms that involve motion, as you can see on the screen, right? Some of the terms that we're going to come across are displacement, distance, speed, velocity, acceleration. Now, motion can be classified in two senses. It can be classified as linear motion and what we call projectile motion. For this uh, aspect of the course, it will be mainly centered for this part, or for this video, I must say, is going to be more centered around talking about the linear motion. So the objective is for us to explain this distance, displacement, speed, velocity, and acceleration. So when we talk about motion, we shall discuss the way in which the position of a particle varies with time. All right. So let's start off by looking at this example here. Here we have a graph showing an ant that clearly, is traveling some distance, right? So the ant is traveling this path just to find a piece of sugar, right? Now, in physics, we refer to this as the distance, right? And distance is the actual length that something has taken, or an object has traveled, so to speak, right? Now, if we remember from uh, in fifth form, or even when we're talking about scalar and vector quantity, we know that distance should be a scalar quantity. The reason behind that is that when we look at the example here, it is so hard for us to get a direction in which this ant is actually moving. All right, as you can see, there's some amount of curvature along the way, so it's hard for us to depict that. Now, to make life a little bit more easier, we as physicists have derived another term which is known as displacement. And what displacement really tells us is, or in general, displacement speaks to a change in position. All right. Now, this ant is at a position on our graph. So this is our XY graph, by the way. So this is the Y and this is the X-axis. Now the position that this ant is at in terms of the coordinates, or in terms of the coordinates, it would be 2, 1, where we know we generally write the X value first, or the X point first, and the Y point. So this is the point that this ant is at. Now, when this ant moves itself to another point, right? That ant changed his or her position to, let's say, this is 5 on the x-axis and 6 on the y-axis. Good. So overall, we can see that there's a change in the ant position. Now, we refer to this change in position as displacement, right? So as the word suggests, displaced, it has moved from one position to another position. All right. Now we can also define displacement as the shortest distance between the starting point and the ending point. Now if we should use position 2 1 as a starting point. So if here is a starting point, good, and the ant final point is here, or the finish point, final point, then that distance is what we would refer to as the displacement. So measuring that distance from the starting to the end point would be referred to would be referred to as what we call the displacement. Now, displacement, as we know, is a vector quantity, and a vector quantity has a magnitude and a direction, right? Now, when as it relates to the magnitude, we could simply use a ruler to measure the length, because the unit for displacement is, so we could use a ruler to measure the length. If we measure that length from where he starts, right? So this is going to be the magnitude. So whatever length we get here is going to be the magnitude. And we can use the Pythagoras Theorem, which we will look at to find his, well, not the Pythagoras Theorem, well, some trig ratios we could use to find his direction, right, from where he started to where he ended. So our direction would be somewhere on this side. So that would cover what we need to know so far in regards to displacement. All right, now let's see. Let me go back a little bit in regards to displacement. Right, remember when I had originally, when I said that the starting point, the coordinates here is 2 1, where this was, let's call this x1, let's call this y1, and the end point has a coordinate point of 5 6 6, right? This one is y2, this is x2. Now, seeing that displacement is changed in position, because we refer to displacement as change in position, what it really means is that the final position must take away from the initial position. Now if we look at this, right, the we're gonna have two displacement, so to speak. We're gonna have one displacement for the y-axis, and we're gonna have one displacement for the x-axis. So let's see. Let's see what value we get for the y-axis. Okay. So for the displacement, for the y-axis now, or we call it the y, let's call it y displacement, that is equal to to y, 2 minus y1. We know y2 as 6 minus 1. Our displacement here for the y is going to be 5 centimeters. Is going to be 5 minus let's just rewrite this a little bit, seeing that we lost connection just now. So we had said that the y displacement is 6 minus 1, which gives us 5 centimeters, and we said that the x now, the x displacement is going to be what was that again? Y2 is 5, or not y2, I mean x2 rather is 5, y1 is 2, so that is going to be 3 centimeters. Now, in order for us to find the exact displacement, so there are two ways we could do it. We could actually measure the length, or we could use the Pythagoras theorem to find out what is going to be the actual displacement. So for us to do that now, we would use the Pythagoras theorem, because what this is telling us is that the change in position for the vertical axis is 5. So from here, from 1 where he started to 6, that difference would be 5. Now on the y-axis now, there's going to be a difference as well. So he moved from position 2 on the y-axis to 5 centimeters. So we end up having 3 centimeters in between here. Good? So we have 5 here, and we have 3 here. Good? So we can now use the Pythagoras, because this has formed a right angle triangle. We can use the Pythagoras theorem to determine what will be this displacement for the side of the triangle, right? So Pythagoras theorem would have stated to us that a square plus b square is equal to c square. We know that c is this side. Let us call 3a, and let's call this side b. So if we go ahead and drop that in our equation here, if we put that in our equation, we know that 3 square is 9 plus 5 square, that's going to be 25, is equal to c square. We're just one step ahead, one step away from getting to find our final answer. So we'll sum 9 and 25, we get 34 equal to c square. Let's just make c become the subject by finding the square root of both sides. Square root of 34 gives us approximately 5.8 centimeters. So what this tells me is that c is now 5.83 centimeters. All right. So that's just the displacement at this point. Now we can find the angle by using some trig ratio. let's just use tan. Let's use tan to find the angle. So tan of the angle is equal to opposite over the adjacent, right? Now, here's our angle that we are working with. If that's our angle, then this side is going to be the opposite, this side is going to be the adjacent. So we have 5 divided by 3 is equal to tan of the angle. 5 divided by 3 gives us 1.6. So tan inverse, shift tan on your calculators, that gives us an angle of about 59.03 degrees. So this is our angle, right? So we can use this method to find all that information, so to speak. All right. So that's that on displacement. Now let's look at speed. So what if this ant that is moving here, you know, somebody had recorded the time that the ant took to travel that distance that we saw, um, to get to the piece of sugar or a piece of candy, right? Then we could actually calculate the speed of the ant, right? In order for us to do that, we would have to use some type of card to measure the distance. So if this is where the ant is going, in order to get this distance, we would have to use some cord, and then after getting that cord to measure the actual distance, then we just put that alongside a meter ruler to measure it up properly and all of that. But let's see. So in order for us to find the average speed, it is defined as the total distance traveled divided by the total time taken. Good. Now this is our equation here. Quite a straightforward equation. Now, as in regards to, let's see, we know that whenever we measure distance, there is no specific direction. Good, hence the reason why uh, speed has no particular direction associated with it. Now, physical quantities such as distance, speed, and time, right? They have only magnitudes and no specific direction, so to speak. So that's why we classify those as scalar quantities. If we were supposed to gather some data from an object traveling a particular distance over time, we can analyze, we can study it by putting that information on a graph, right? Now we're seeing two lines, two separate plots here. The one in red is showing us some information. We'll look at that shortly. And yeah, it's showing us some information here. The blue line is showing us some information as well. Now, let's look at the red line first, right? So it's clear that this object, from its initial position, right, from the starting point, which in my estimation is 0, starting from 0 all the way to 8 meters, that object we can say was speeding at a steady rate, right? So when we say speeding at a steady rate, it means that either, so for example, it's a car. That car would be speeding, or that car would be changing its distance at a constant rate. So for every, imagine, so take for example, for every 2 centimeter the car travels, it took the car 1 second to do so. So let's look at it now. 2 meters on my y-axis correspond to 1 second. 4 meters on my y-axis correspond to 2 on my x-axis. So this is telling me that my car is moving at a steady speed, right? And one way to even find this out too is by finding the gradient of this graph, right? But we know, let's look now. So it's clearly this section from 0 to 8 meters, that car is at a steady speed. Now when the car reaches 8 meters, it's clear that the car is no longer changing distance. The car has stopped, right? So because the car has stopped, we refer to that as being stationary, because remember now, you are not changing distance anymore. So if you're not changing distance, that means you're at zero distance, I guess. And with that, you cannot find a speed, because speed is related to distance traveled over time. So once there's no distance, then you pretty much doesn't have a speed. So you are stationary, or the car has stopped in some cases. Now we can look at it from that standpoint. All right. Let me see. Now when we talk about speed, right? Speed can be referred to as instantaneous in some cases, and I just made mention of steady speed. Another way we can say is uniform speed, and uniform speed occurs if an object covers equal distance in equal time intervals, no matter how small the time intervals are. So that would be uniform speed. So the car has a uniform speed from 0 distance to 8 meters. Now, instantaneous speed is another term that we can come across, or we will come across in physics. So imagine if I want to take a synopsis of when the car reaches 6 meters, then it is for me now to zero in on what is happening at that point. So if I said, what happens when the car is at, or what is the time when the car is at 6 meters, then all I would have to do is to look at my graph and see what value it corresponds with, right? And based on that value is 3. So it means that my instantaneous speed at that point is going to be 6 divided by 3, right? So yeah, we can look at an object in an instant to find out what is happening there. So this is going to be 2 meters per second, all right? Grant you is that if you go anywhere else to find out what is happening at any point on your curve, you're going to get the same thing because of the nature of this line. Now if we look at another one here, the blue line now is, we can see that it is at a steady speed, uniform speed, straight line going all the way up. I would assume that it would continue, unless something acts upon it, like slow it down or something of that nature, right? Now we can look at this to say that this speed in blue is more rapid than the speed at in red, right? Because of how steep this line is at the blue section. The blue section is much steeper. It has a much steeper gradient. So we can say that that car is going to have a much higher uh, or much larger, I must say, speed than the one that is in red. All right. Now, from our knowledge regarding to speed and velocity, right? Let's look at what difference they have from a graphical standpoint, or in terms of their categories that they fall into. Let's look at velocity. So velocity is defined as the rate is defined as the rate of change of position with time. Remember, when we talk about rate of, or we talk about change of position, or initially we talked about displacement. So this change of position speaks to displacement, and we know when we're talking about rate of change, time is involved, right? So with that, guys, so there's a thing about physics. Most definitions, right? You can pull a formula from the definition, and that is what we have just done, because the two variables that they speak of here is change of position, which is displacement, and time. Hence why we say that velocity is equal to displacement divided by time. Having said that, it says since change of position is called displacement, to calculate the velocity, we we divide the displacement by the time taken. Note that unlike distance, displacement has a specific direction. Good. And velocity has the same direction as the displacement. So guys, it is the displacement that allows velocity to have a direction. Just remember that. And we did talk about, displacement having a direction already, and how we were able to find that when we looked at the example above. Now here we have some graphs. Let me see if I can make it a little bit bigger. Now let's look at these graphs here. So these graphs are all velocity time graph, not velocity, displacement times time graph, right? But we can have different types of velocity graphs, as you can see. Now the first one here is telling us that there is zero velocity, right? Which means that the object is at rest. Now, just want you to know that this object doesn't have a displacement. While you might see, because generally we start our graph at 0, and we increment by some value. So if this is 8, good, that object is at the position 8 meters from now until die kingdom. So because we know that final uh, final position minus initial position gives us displacement, then this tells us that if 8 is my initial position, and 8 is my final position, then clearly there's no displacement, there's no change, so that is going to be 0 meters. So that's why we can say that the velocity is 0. And in other words, the object is at rest. Hello. The slope is going to be 0. Let's look at another example of a displacement versus time graph. Now, this one here, the second graph is more similar to that of the one that we saw, a distance versus time graph, uh, when we looked at speed, right? So it's almost telling us the same thing. The only difference is that we're dealing with a vector quantity here, so we expect that there's going to be some direction, so to speak. So clearly our slope is positive, right, from this, because we are moving upwards, right? So whenever we're going up the y-axis, we refer to that as being positive. Now, as regards to the velocity here is constant, meaning that for every second I travel, I cover the same amount of distance, or it's like that, right? Where it's in a uniform way, so to speak. So it's like you driving a car and you maintaining a steady rev, or you're driving in such a way that you are not uh, increasing speed. So you could see something saying like 30 kilometers per hour. So that's what your velocity is, so to speak. All right. Now we can look at another graph here. This one, this we will come across these kind of graphs where the slope will look like this. What this is telling us is that the slope is going to be negative. So whenever we descend or have a position versus time graph looking like this, then we expect that the slope is going to be a negative value, because we perceive things as going, when it's going down in physics, as being negative. Hence why we would say our slope here is negative. And from the mathematical standpoint as well, it would be negative. If here's my starting point and here's my ending point, when I do my maths, so you know, it would give me a negative value, so to speak. All right. And clearly, based on the type of line that we have, the straight line looking thing, graph that we have, we can say that our velocity is constant. Now, there are times now when our velocity, our position versus time graph can be, what do you call it now? It can be a curve, right? And in this case, the velocity is not constant. So our velocity is changing, uh, so to speak. And if our velocity is changing, it means that acceleration is going to be a thing that we will need to talk about, right? So once your position is changing, right, then you you will expect that your velocity is no longer constant, right? And as of such, we can say that the car or the whoever is moving is accelerating. As we speak about acceleration, let's look at what acceleration is. So acceleration is the rate of change with time, right? And in order for us to, we can just go ahead simply and write that based on the definition, we can come up with a formula that would say velocity over time is equal to acceleration. Now, when it comes out the average acceleration, we would have to take into consideration the initial velocity and the final velocity, and divide that by the time it took that object to accelerate. That's how you would find the average velocity. And that is similar to finding the gradient, so to speak, right? Yes, that is similar to finding the gradient. as you can see in this formula here. Now this is how this type of graph here is showing us different ways in which acceleration can be displayed. We can have a positive acceleration. This positive acceleration is going to be constant acceleration, or we'd say uniform acceleration as well. And we can understand uniform when we say uniform acceleration or uniform velocity, it means that it is constant. So for every change I make, the increment is the same with respect to the time. All right. Now there's a point now when there's no acceleration, and this is when my velocity is not changing. Right. So whenever your velocity is at a constant rate, in this case where our velocity is 8 meters per second for a time period of let's say 3 seconds, right? From 4 to 7, the car or whoever is not accelerating, but it is actually moving steady, or would say constant velocity, right? Now, initial as we mentioned of when we're decelerating or whenever we're going downwards, and whenever there's something going downwards in terms of graphs, right? That's going to be negative. So our gradient, if we're supposed to calculate a gradient for this, then this is going to give us a negative value. Anytime we have a line, a straight line going downwards like that, right? That's going to be a negative gradient when we do calculate it. So we have negative acceleration, or in some cases we say deceleration, right? So when you hear about decelerating, it means that the car is either slowing down or coming to a stop, so to speak. All right. Now let me see. Let's look at that example. Um, that says a car traveling at 36 kilometers per hour on a straight level road come to a stop in 2 seconds. It says calculate the average acceleration of the car during the 2 seconds. All right, so in order for us to tackle a question like this, guys, we have to bear in mind that we're dealing with average velocity, right? So average velocity, not average velocity, I mean average acceleration is equal to um, final velocity minus initial velocity divided by the time, right? Now, let's see what this question gave us. So clearly, we got the initial velocity or the initial speed. So we now need to convert this right here. We now need to convert this right here into uh, velocity. And how we can do that is by simply doing this. So 36 kilometers in terms of velocity would be multiplying the 36 by 1000, then dividing that by uh, 3600, because we know that 1 hour is equivalent to this in terms of seconds. So this is now transformed into that. So when we do that, we get a velocity of 10 meters per second. Having said that, we now know that our initial velocity is 10 meters per second, whereas if we look at the question, it says that come to a stop at 2 2 seconds. This is telling us that the final velocity of the car is 0 because it came to a stop. Now that time taken is 2 seconds. So, having said this, having found out all of this information, we can now go ahead to finish up our problem by saying the average acceleration is equal to negative 10. I'm going to do something here. I'm going to put, whenever we have this thing, seconds to the minus 1, it can be rewritten as such. You can take this and bring it down in the denominator so that you can understand how we get the formula, or the unit rather, for acceleration. So by putting that down into the denominator, I'm left with 2 seconds times another second, right? And if we do the maths, this is negative 5, right, times meter divided by meter square. Hence now why we get meter square, you understand? For acceleration, because we know that this is the unit for acceleration, right? Yeah, so this is a quite simple question, nothing hard. Now we see the negative here. This negative is just giving us information in regards to the direction. Because remember now, when you're dealing with vector quantities, a direction and a magnitude must come into play. The 5 is our magnitude. And the negative now tells us that it is decelerating, right? Even though it says that the car is on a straight road. Even if you're on a straight road, you can decelerate. You understand? Yeah. So that is about it in regards to this thing here. Now, when we do continue our lessons, we will be looking at equations of motion for constant acceleration, right? Now, at this point in our graph, this is when we're having constant acceleration. This kind of straight looking line going up like that's when we're having constant acceleration, right? So we're going to look at some equations that we will apply throughout the duration of this aspect of the course, so that we can appreciate, motion some more, right? And have an appreciation of how these things work, so to speak. So we'll look at that in the subsequent lesson. Nothing far from where we have started with so far. We're just going to derive some formulas and so forth.